Two aircraft are flying eastwards around the Earth. Aircraft A is flying along 50° north latitude. The second aircraft is flying along the equator. If the speed of first aircraft is 340 knots, what would be the speed of aircraft second, aircraft Bravo, if both aircraft fly around the Earth in the same journey time? Okay, so I have done this type of questions many times in my other video lectures. So the first aircraft is flying along 60° north parallel of latitude, 50° north parallel of latitude. And when it flies along that fixed 50° north parallel of latitude, it will make a 360° rotation, a complete 360° rotation on that particular latitude. So the distance that it will cover, or the distance it will in turn travel in covering the full 360° rotation around the Earth, will be equal to the Rumline distance. And now what is Rumline distance? Rumline distance is d long in minutes into cos lat, correct? This is your Earth, let's say, and you have 50° north latitude, 50° north latitude. An aircraft is going to encircle the Earth around this latitude, around this latitude, correct? Around this latitude. So drumline distance will be d log in minutes. What is the total difference in longitudes when you make a complete 360° rotation? It is 360°. You start at one longitude, make a complete 360° rotation, and come back at that same longitude. So distance is 360° into 60 into cos of latitude cos 50. So drumline distance will be equal to cos 50 multiplied by 360 into 60, 13,884. 13,884 nautical miles. Now the ground speed is given to you. The ground speed of this particular aircraft is 340 knots. Now when you know the speed and distance, you can easily calculate the journey time using speed distance time formula. So 13,884 divided by 340. 13,884 divided by 340 is 40.8 or 41 nautical miles. 41 hours. 41 hours. So the journey time is 41 hours. Now in the second situation, there is another aircraft which is going to encircle the Earth around the equator, equatorial latitude, 0° north-south latitude. So there is a 0° north-south latitude here, let's say. Okay, so there is another aircraft which is going to encircle the Earth at this latitude, correct? So again, you will have to apply Rumline distance d log in minutes into cos of latitude. So 360° into 60 into cos of 0. 360 into 60 is 21,600 nautical miles. The speed, the time available to this aircraft is the same journey time that was taken by the aircraft number 1 in encircling the Earth at 50° north latitude. So that is 41 hours. Ground speed of the second aircraft will be distance divided by time. Distance is 21,600, time is 41 hours. So 21,600 divided by 41 is 526.8, that is 527 nautical miles per hour. So the ground speed of the second aircraft is 527 knots. It is 527 knots. Okay. Next. Question number 12. When landing on runway 36 in North Hemisphere, a direct reading magnetic compass will indicate what? So our magnetic compass subject to two kinds of errors. The first one, turning errors, okay, turning errors which happen at north and south headings. Second is acceleration and deceleration error, which happens at easterly and westerly headings, which happens at easterly and westerly headings. Now you are landing on a runway which is oriented 360 and in the northern hemisphere. So a compass will indicate what kind of error. It will indicate turning errors. On north and south headings, you get turning errors. Okay, next. So next is east-west, you have acceleration, deceleration errors. Now, let's say this is your north datum, okay, and here is your runway 36. This is runway 36, this is runway 18. Now, when this aircraft is landing on this particular runway 36, it will be oriented with this runway 36 and it will land straight ahead on runway 36. Now, these turning errors happen on north-south headings, that is correct, but your aircraft should be turning. So, let's say this is your north datum here, like I said, an aircraft is turning from northwest heading, then to north heading, and then to northeast heading like this. So from northwest, north, northeast. So when you make a turn around the north pole like this, you will be subject, your magnetic compass will be subject to turning error. Similarly, when you try to make a turn around the south pole like this, from southwest, when you are turning your aircraft from southwest heading to south and then to southeast, again you will be, your compass will be subject to turning error. But in this case, in the case given in the question, your aircraft won't be turning because it is coming down to land. It will land straight ahead, so there is no turning of heading over here. So magnetic compass will not show any kind of a turning error. So the correct answer here is option C, no turns. Question 13. Magnetic heading can be calculated from the true heading using what? A compass and a map indicating isogonal line, a compass and a calibration card, a compass and a deviation card. Okay. So you want to obtain magnetic heading from true heading. So the link between a true heading and magnetic heading is variation. Okay. So if you want to derive magnetic headings from true headings, you will have to make use of variation lines shown on the charts that you are using, VFR, IFR, whatever. So isogonal lines are nothing but lines joining places of equal magnetic variation. So whatever chart that you are using, let's say national chart in the US, and you can see a magnetic variation line, this one. This particular magnetic variation line, this red colored dash line, and it's written 7 degree west. 7 degree west is also written here. Okay, 7 degree west is written. Okay, so this line is your isogonal line. So any aeroplane flying in this particular area will use that 7 degree west variation and convert his two headings to magnetic headings. Now, magnetic headings can be converted into corresponding compass headings using your magnetic compass and the deviation card that comes along with it. So that is for compass heading. But for magnetic and true, it is isogonal line. So option A is the correct answer. 14. Errors in direct reading magnetic compass can be caused by what? So like I said before, there are two types of errors. The first error is the turning error. The turn errors occur when you turn your aircraft around north heading, around north and south poles. So you want to turn your aircraft from northwest heading to northeast heading. So you will be passing through the nearest north pole or the northerly heading. Next is acceleration deceleration error. Acceleration and deceleration error. So when you accelerate on easterly or westerly headings, or you decelerate on this east heading or west heading, your aircraft compass will again be subject to some error called acceleration deceleration error. So that happens on east and west magnetic headings. Remember this fact. So errors can be caused by turns through 90 degrees east and 270 degrees west. That is wrong. Turning errors are caused through North Pole and South Pole. Acceleration on east and west headings, yes. Crosswinds when on east and west headings, no. Crosswinds do not cause any kind of compass error. It will cause drift, but not error in magnetic compass. So option Bravo is the correct answer. In aircraft taking off on runway 27 in the northern hemisphere, what will its direct reading magnetic compass indicate? So direct reading magnetic compass is subject to two errors, turning errors and acceleration deceleration error. Now here for this particular question, we are going to focus our attention on acceleration and deceleration errors. Now look at the runway number here. So we are taking off from, this is your north datum. We are taking off from runway 27. So this is runway 27. This is runway 09. Okay. So you are taking off from runway 27. So when you take off from runway 27, you will take off from here and go in the westerly direction. You will go in the westerly direction. Now the most important part of a takeoff is accelerating your aircraft, accelerating your aircraft. So whenever you are ready for takeoff, you release your brakes, apply full thrust, takeoff thrust power, and then you start rolling down the runway. You accelerate your aircraft. When you reach enough or sufficient acceleration speed, you are ready for liftoff. So whenever acceleration happens, there will be some error called acceleration deceleration error. Now whenever you accelerate in the northern hemisphere, whenever you accelerate in the northern hemisphere, okay, accelerate flying west or accelerate flying east, whatever. So whenever you accelerate, the magnetic compass will point towards the north heading, will point towards the northerly heading. So first you are oriented with the 270 heading, but when you start accelerating, the magnetic compass will tend to show a direction which is close to north heading. So instead of showing the correct accurate value of 270, the compass will tend to show values of 300, 310, something like that. So that is one problem or one error of this magnetic compass. So in an aircraft takeoff from runway 27 in the north hemisphere. So if you are in the north hemisphere, the turns will be towards the north pole. If you are in the southern hemisphere and you accelerate on east heading or west heading, the turns will be towards the south pole. So here you are in the north hemisphere. So the turn will be a northerly turn. Very important. When deceleration, now let's say you are in the northern hemisphere, you're oriented westerly heading or easterly heading, whatever, but you decelerate your aircraft, you slow down your aircraft, let's say after landing. Once you touch down, your aircraft will start decelerating. So when your aircraft starts decelerating, in that case, the magnetic compass will start showing a turn towards the south. So instead of pointing towards 270 or getting aligned with 270 magnetic heading, the magnetic compass will show a heading of let's say 290, correction 240, 230, 250, any direction in the southwest. Okay, so something the tendency is towards the south heading. Okay, so that is one important thing. The rollout must be performed at dash heading when turning from northwest to northeast in the southern hemisphere. Okay, so very important turning error. This is your south pole, let's say. Southern hemisphere, this is the south pole. And you're turning your aircraft from northwest to northeast. You're turning your aircraft from northwest to northeast. That means this is your aircraft oriented northwest. Okay, you want to turn it towards northeast like this. You want to turn it to northeast like this. So you will start turning your aircraft from northwest, then align it with the north heading like this, and then you will turn right hand side again and align it with northeasterly heading. So the turning error will be something like this. When you are in the south hemisphere, when you are in the south hemisphere, so pay attention to the position, whether you are in the north or south hemisphere. The turning is around the opposite pole. So here you are in the south hemisphere, but despite of that fact, you are turning through the north pole, opposite pole. So turning is around the opposite pole. In this case, it's the north pole. So the consequence will be the magnetic compass will be overactive. Okay, it will be overactive. So whenever you turn around the opposite pole, so the compass becomes overactive. Okay, even if you're turning at a moderate rate, the magnetic compass will be running ahead of you. So the solution is that you will start rolling out your aircraft much before you have achieved your desired heading. So let's say your desired heading is 050, northeast heading 040050. So even before reaching that heading, you will start rolling out your aircraft. Okay, or correction. This is overactive. So once you rollout must be carried out, rollout must be carried out later. So your desired heading is 040, let's say. You know that magnetic compass is overactive. You are turning your aircraft at a moderate rate, but this magnetic compass is behaving overactively, so it is running ahead of you. So you may be aligned with the heading of 030, but magnetic compass will show 050. So it's showing a direction which is more than required, more than the expectations. So in such a case, you will roll out your aircraft, you'll start rolling out your aircraft, unbanking your aircraft after you reach your desired heading. So your desired heading is 040. You will start banking out your aircraft at a heading which is later than or beyond 040, like 050, 060, something like that. Okay. So rollout must be executed much later. So you know that when you start rolling out much later, by the time you complete your rollout, your magnetic compass will come back to the original heading of 040. So first it was showing 050, but when rollout is completed, it will show 040 because once you complete your rollout, the turning error will disappear or the turning error will go away. So rollout must be carried out later because magnet is behaving overactively. So here the rollout must be performed. The rollout must be performed at dash when turning from northwest to northeast. So rollout must be performed later. So let's say northeast directions are normally 040, 050. So you will perform your rollout later. So option Charlie, 055, 10 degrees later. Question number 17. A perfect straight line on a Lambert chart are meridians. So meridians are straight lines or Lambert chart. Remember all the properties of all the charts. How do rhumb lines other than meridians appear on polar stereographic charts? So this question has been asked many times before. So rhumb lines are lines concave to the pole of projection. Question 19. What is the time to the point of safe endurance, that is point of safe return, if aircraft has a so and so task 300 knots, endurance 4 hours, wind component going outbound is 20 knots headwind. So let's say this is point A, this is point B. You're going from point A to point B. This is your point of no return. Now going outbound from point A to point B, you are getting a headwind of 20 knots. Coming inbound, that is when you make a decision of coming back to your departure airport at or before point of no return, your aircraft will be experiencing tailwind. The same wind will act as a tailwind now. Now going outbound, your task is 300. So ground speed will be 300 minus 20. So headwind. So headwind, that means we are getting a headwind of 20 knots. So ground speed will be true airspeed minus headwind. So 300 minus 20 is 280. Coming homebound at the same task of 300 knots, the ground speed will become 320. So in case of tailwinds, you add the wind component to get a ground speed. Now let's employ the formula for distance to PNR, which is endurance into outbound speed into homebound divided by outbound plus homebound. Endurance is 4 hours, outbound speed is 280, homebound speed is 320. So here the speeds that we are talking about are ground speeds divided by 280 plus 320. So 4 into 280 into 320 is 358,400. 280 plus 320 is 600. 358,400 divided by 600 is 597 nautical miles. So distance to PNR is 597 nautical miles. Time to PNR will be distance to PNR divided by outbound ground speed. So 597 divided by outbound speed 280 knots. 2 hours 8 minutes. 2 hours 8 minutes. The closest option here is option Charlie. Correction to 2.1. 2 hours 8 minutes is equal to 2.1 hours. Point 1 equals to 6 minutes. Point 6 will be equal to 36 minutes. Point 9 will be equal to 54 minutes. So the answer that I have got is 2 hour 8 minutes. So the closest option is option A, 2.1. Next, maximum allowable tailwind component for landing is 10 knots. Runway is 05 or accurate value is 047 degree magnetic. The direction of surface wind is 210 degree. Now all ATIS winds are true. ATIS winds are reported in true direction. That's why variation is also given to you. Calculate maximum wind speed that can be accepted without exceeding the tailwind limit. Okay. So the formula for a long track component is minus in case of headwind, wind speed into cos theta. Theta equals to wind velocity minus runway direction. Now here wind velocity is 2102, variation is 17 east, east is least, so 210 minus, so variation 210 minus 17, so magnetic will be So 1903 minus runway direction 047. Use the accurate value 146. So winds, so along track component, tailwind limit is 10 knots. So 10 knots equals to wind speed that we have to find out into cos of 146. So wind speed will be equal to 10 divided by cos 146, which is minus 0.83. That is 12 knots. Minus minus cancelled, so 12 knots. So wind speed will be equal to option A, approximate 11 knots, or accurate value that I have got is 12 knots. So this is how you do this sum. I hope you have understood all the 10 questions that I explained in this particular lecture. In the next video lecture, I will be solving the next 10 questions. So don't miss that video lecture. I request you all to share this video with your friends who are also preparing for the exams. Subscribe if you haven't yet, and hit the like button if you have liked this video lecture. Thank you.